Yeah, now I'm recording. Okay, perfect. So here's the first example. So let's say you have say, 6 to the power x minus 1 equal to 6 to the power minus the x plus 2. All right. So this is an exponential equation because, as you can see, on both sides we have this exponential in base 6, right? This is an exponential. This is like b to the x, right? Where b is equal to 6, right? So this is an exponential, and the same thing here. So so both sides are exponential with base b equal to 6, are exponential with b equal to 6, right? Now, in this example, so both exponential functions, they have the same base, right? We have the same base. This is base 6, and this is base 6. And we said actually when you have the same base, then the powers are equal. Okay, so this is so when the bases are so when you have the same base, then the powers are equal, or the exponents are equal. So on the left side, the exponent, of course, is this x minus 1, and on the right side the exponent is minus the x plus 2. Okay, so the exponents are equal, so then x minus 1 is equal to this minus the x plus 2. Okay. And so, and actually this is not really hard to solve, right? I mean, you can add, let's say, plus the x. So move the x on the same side. So I'm going to add, this is minus the x. I'm going to add plus the x both sides. So then that would be 4x on the left, minus 1, minus the x plus the x, cancel out. So it's just plus 2 on the right. And then I'm going to move minus 1 to the other side. So minus 1, the opposite operation would be plus 1, of course, both sides. So that would be just 4x equal to positive 3, right? And then last thing to do, that's 4 times x, so opposite operation will be division, so we have to divide by 4. So that's just x equal to 3 over 4. The good news, guys, is that exponential, exponential functions, they're defined for any real number x, right? b to the x, the variable x can be any real number. So the domain is the whole number line, right? So here there's no condition to check. There's nothing to check here. So this is like the fine answer. So fine answer. So x 3/4 is the solution of the problem. Is the solution. Okay, so that's why I said in some sense, like exponential function equations are kind of easier than logarithmic equations, right? So there are no conditions to check here, because exponential are defined for any real number x. That's different from the log. Okay, so any question, guys? Well, this is, of course, this is the case when we have the same base, right? So we're gonna see another example, like when we have like different bases. What happens if you have different bases, right? Let me do sorry. So let me do one more example. Example number 2. So let's say you have example number 2. So let's say you have 5 to the power, let's say 2x minus 4 equal to 1. Okay, Well, I mean, on the right side, it's just the whole number one, but on the left side, we do have an exponential. So this is why it's an exponential equation here. So there's this exponential, as you can see, exponential with base 5. This is an exponential with base b equal to 5. Oh yeah, sure. Is this okay, Lorden? Okay. Okay, perfect. So yeah, so this is exponential with base b equal to 5 on the left side. As I said, the right side, it's the whole number one. So the question probably for you guys, do we have the same base on in both sides? The thing here is that you can write, so the idea is that you can write one as 1, you can write it as 5 to the power 0, right? I mean, any non-zero number power 0 would be equal to 1. So I can write 1 as 5 to the power 0. And now, as you can see, both sides, I have the same base, right? So now I have like the same base. Okay, and again, so because we have the same base, then the powers are equal. So the power on the left side, or the exponent on the left side is 2x minus 4, and the exponent on the right side is actually 0. So the exponents are equal, so then 2x minus 4 is equal to 0. Okay, and then of course, then x would be equal to, so 2x would be equal to 4, and so x would be equal to 2. And that's the final answer. So x is equal to 2 is the solution. So you see, guys, even if the right side, it's just like a whole number, which is 1, you can write it like, 5 to the power 0. So then again, we have like same base, and then so the exponents are just equal. All right, so now next question, or next big question, is what happens if we have like different bases? So for example, so example number 3. So this is, let's say 4 to the power 2x minus 1 equal to 3 to the power x plus, let's say x plus 2. All right. Well, this is again an exponential equation, because on the left side we have an exponential function, the base b equal to 4. Right here, the base is so the exponential, the base b is equal to 4, and here exponential with base b equal to 3. All right. So here in this case, the bases are different. And that's a kind of a problem, because if the bases are different, you cannot say that the exponent are equal. Okay, so so here we need to be careful. So this is like a, bases are different. One is a basis 4, the other one basis 3, right? So the bases are different, so we cannot say that the exponent are equal. Okay. So how do you solve such an equation, right? The problem here with this equation is that your x is in the exponent, right? Is in the power. And so you need to bring down your x, right? You need to bring down your x because if your x is the exponent, you cannot really solve your equation, right? So the idea here, to solve such equation is to bring down the powers. So x, the variable x, so the x is in the exponent. So we need to bring down the x. Okay, so we need to find a way, to put down the x. We need to move it from the exponent to somewhere in the equation, right? So how do we bring down the x and the exponent? Well, the idea is to use one of the properties of the log. So remember, one of the properties of the log. So if you have like log, in some base b, like x to the power some power a. Okay, then if you have like something in the power with the log, then you can put down your power a in front of the log, right? So this would be like a times log in base b of x. So we're gonna apply exactly this formula to our equation. So the first step here, so whenever you have an exponential equation with different bases, so the first step is to apply, step one, we need to apply natural log. Okay, again, natural log, that's the log in base e to both sides. Okay, actually you can apply the log in any base. It doesn't matter which base you're gonna apply your log, because if you here I'm gonna apply natural log because it's like sort of a convention, because the log in base e, that would be like the natural log to use. But the idea is just apply log in some base, so then you can bring down your exponent x. So I'm gonna apply, so in this step, so we have this 4, we have on the left side, we have 4 to the power 2x minus 1, right? And on the right side, we have 3 to the x plus 2, right? So this is 3 to the x plus 2. So what I'm gonna do, I'm gonna apply natural log to both sides. Okay. So what does the natural log do? Well, the thing is, you can, so then you can bring down this power, this exponent in front of the log here. Okay, so then that will be 2x minus 1. Okay, times, so if you bring down the 2x minus 1, then you are left with, well, don't forget there's a log here, natural log, this natural log here, and that will be natural log of 4. So 2x minus 1 times natural log of 4. And again, natural log of 4, it's just in some number. I mean, if you have a calculator, you can try to see, you can check what's the natural log of 4. It's just some number, some decimal. Okay, this is just some number. So you think of it as some number. Okay. And on the right side, it's the same thing. So I'm gonna bring down this x plus 2 times. So now on the right side, that would be natural log of 3.
I have a question, Professor.
Yes, please.
So anytime that we see this problem, can we just like automatically think, okay, boom, we could just put it in front of the log and that's it?
Yes, yeah, but you need the log, right? So you need to apply the log first, and then you can then put down your exponent in front of the log. So as Rabiu said, I think, yeah, so log, like log of 4 is gonna be like 1.386, and log of 3, that would be 1.098 or something. Thank you, Rabiul. So yeah, it's just some, so it's just some decimal. So this is like 1 point, Rabiul said, so this is 1.386, and this is also some number, some decimal. It's 1.0 something. Yeah,
Yeah.
98. Okay.
I have to put that.
Yeah, no. That's what I'm saying here. Just keep the natural log of 4, because I think it's not really it's not really convenient to use the decimals, right? So it's better to just keep the natural log of 4 instead of the decimal, because the decimal will be like 1.386. So you have to carry this 1.386 along the equation, and that's not really a good idea. I think just keep the natural log of 4. I mean, it's more compact way to describe the number, I would say. Yeah. But again, just think of natural log of 4 as a number, so some number, okay? So now, so how I'm gonna solve for x? Well, I mean, natural log of 4, natural log of 3, just some numbers. So then I can distribute and, distribute and then try to solve my x for my x. So like here, it's like this 2x times this natural log of 4. And then there's this 1 times this natural log of 4, right? And on the right side, it's like this x times this natural log of 3. And then this is 2 times this natural log of 3. Okay, so on the left, I have 2x times this natural log of 4. And there's this minus. So here's minus 1 times natural log of 4. And on the right side, it's x times this natural log of 3. And there's a plus. So it's 2 times this natural log of 3. Okay. All right. So it's just some equation with the x. I have an x on the left side. There's this x here, as you can see, on the left side, and there's another x on the right side. So all I have to do is just to to move all the x's on the same side and everything else to the other side. So what I'm going to do, for example, this is x times natural log of 3. So I'm going to subtract same thing. So it's minus x natural log of 3. And here, minus x times natural log of 3. Okay, so I'm going to move the x's on the same side and the constant to the other side. Okay, so again, guys, don't be scared from this natural log of 4, natural log of 3. It's just some decimals, right? Think of it as just like a number, like 2 or 3 or 4. It's just some number, right? Now, on the left, I'm going to have like 2x times this natural log of 4. And then minus this x times natural log of 3. I cannot really simplify anything here. Minus, there's this 1 times natural log of 4. I mean, 1 times any number is going to be just the same number, right? So it's just minus natural log of 4. And on the right side, well, I mean, the same thing cancel out. And I am left with this plus 2 natural log of 3. So it's here, it's 2 times this natural log of 3. Right? So as you can see, guys, I got my x's on the left side. You see, there's an x in here, there's an x in here. I can, then x would be a common factor, so I can factor out my x, and then solve for my x. Well, and the thing is, there's still one constant on the left side, this constant, which is 1.386, this natural log of 4, which is some number. So I'm going to move this constant to the other side. So I'm going to add, it's a minus, so the opposite operation, of course, would be plus. So plus. So now it's like 2x times natural log of 4 minus x times natural log of 3. And on the right side, of course, this thing here cancel out this here. And on the right side, it's 2 times natural log of 3 plus natural log of 4. Okay. So as you can see now, guys, on the right side, I have like two times this natural log of 3, which is like 2 times 1.098 plus this natural log of 4, which is like plus 1.386 or whatever, right? It's just some decimal. All right, so now, so what I can do is I can, x is a common factor here. So I can factor out my x. So that would be x times. So if you pull out x here, then you are left with this 2 times this natural log of 4, right? If you pull out x. So this is now here, between parentheses, I'm going to have 2 natural log of 4. And then there's this minus. So here's my minus. And the same thing here, pull out this x. Then you are left with this natural log of 3, which is, again, some decimal. So minus natural log of 3, parentheses, equal to this 2 natural log of 3 plus natural log of 4. All right. So we are almost done because now, well, this is like x times, this is just like x times some number, like x times 3, for example. So how do we solve for x? Well, I'm going to divide by that number, right? So here the number is, of course, it's more complicated than 3. It's with the logs here. So yeah, by the term, absolutely. So I'm going to divide by this 2 natural log of 4 minus natural log of 3. And of course, we need to do the same on the right side. So this is 2 natural log of 4 minus natural log of 3. And of course, because this is the same thing here, so that will cancel out. So it's now just x on the left side equal to this 2 times natural log of 3 plus natural log of 4 over 2 natural log of 4 minus natural log of 3. And that will be the final answer. So this answer is very precise because, I mean, if you replace like your natural log of 3 by this 1.098, right? It won't be precise because actually it's more than that, right? If you use calculator, you're gonna have like a lot of, it's not like there's just the 3 decimals, right? So, yes?
No, sorry, Professor. Go ahead.
Okay. Oh, okay. Sorry, I thought you were asking a question. So yeah, so this would be like the more precise answer here. So this is a final answer, of course. So this is my final answer. And as I said, I mean, you can try to approximate this answer. So what we are saying here is like x is 2 times natural log of 3. We said like it's like 1.098 something. Rabiul, I think you have right. The answer is 2.140. Okay, now thank you, Rabiul. So yes, so plus natural log of 4, which is like 386. So this is like 1.386, over 2 times this 1.386 minus this 1.098. And as Rabiul said, so this should be like 2.140, right? So this is like the answer. But again, guys, the point here is not like to use decimals because, decimals, that would be it's not really convenient to use decimals, right? It's you have like 3 numbers after the decimals. So it's a lot. That would be a lot, I guess. So it's not really convenient. So yeah, so the best answer, I think this is the exact and the best answer is this one here. Okay, you don't have to approximate your answer. I mean, you don't have to compute this decimals because it's not really relevant. So yeah, so that's the answer is just this one here. Okay. Any question, guys? So you see, this is the case when you don't have the same base, right? You have like we had like an exponential in the base 4 on the left and an exponential in the base 3 on the right. So what we do is we apply this natural log to both sides. And as I said, you can apply any log in any base. But we are applying this natural log because this is like the natural thing to do. But the idea is, is to bring down this exponent using the log. Any question, guys, about this example? So I think we covered all possible examples. So when you have the same base, when you don't have the same base, so probably I think we can go for an exercise. So here's an exercise. So this is similar to the homework, the second part of the problem 1 in the homework number 6. As you can see, so exercise. So this is, of course, is going to be in the final. So this is similar to the problem part, the second part of the problem number 1 in the homework 6. Homework 6, problem 1. Second part of the problem 1. I think there's a question in the chat.
I was sending. I just sent direct message by mistake. I'm
okay.
I thought I was chatting to everybody the whole time.
No problem. All right. So yeah. So here's the first equation. So let's say the first equation. Let's start with a simple one. Okay. So let's say you have 7 x squared plus 1 equal to 7 plus 2x. I mean 7 to the power 2x. 7 to the power 2x. Right. Number 2. Let's say now we have e. So again, this number e is just some special number, a decimal. It's the natural exponential. So let's say e to the power 4x minus 1 equal to 3. Okay. And number 3. Let's say we have 6 to the power. Let's see here. Yes, x squared minus 1 equal to 1. And the last one, of course, when you have different bases. So let's say here we have 2 to the power 3x plus 1 equal to this is 5 to the power x minus 1. All right. Okay, guys, let's say you have 10 minutes to think about this exercise. So I would say this is like with the all possible different exponential equations. Okay, so when you have the same base, when you have different bases, and when we have like an exponential on one side and just like a whole number on the other side. You're saying it's one. Yes, Rabiu. Yes, absolutely. Yeah, for number one, the solution is going to be one. Yes. So again, just to clarify, guys, this E is just some. This E is just a 2.71 something, just some decimal. Beth, you see the chat. What did you see?
I was confused if you post the homework, but I saw already. Thank you.
Oh, the homework. Oh yeah, it's on. Yeah, it's on. Yeah, it's on Blackboard. Yeah. Actually, I posted the homework and the review sheet for the final.
Oh, perfect. I'm going to say it.
So actually, I'm not sure how much I'm gonna cover in the trigonometry section, guys. So like in the review sheet, there are like 2 problems about trig functions. I'm sure I'm gonna cover like one of them, but we'll see if if I'm gonna be able to cover the 2 problems in the review sheet. Okay, so it depends on how much material we're gonna do tonight and tomorrow. Joel, yeah, well, I know trig is like a nightmare for all the students. This is getting crazy. I know trig is it's like a nightmare for most of the students, but it's not that bad. I mean, it's just it's just a question of practice. I mean, anyway, we'll see.
We don't have time to practice. What are you talking about? What?
All right, yeah. Yeah. So no, so yeah, the plan is to have like at least 1 hour review tomorrow, and another hour before the final on Thursday. So the final is going to be from 7 to 10:30. So we're going to have review from 6 to 7. It's like if you have like last minute question, I can answer them. So from 6 to 7 there'll be a review, And tomorrow we're gonna also have a review, at least 1 hour. Again, it depends on how much material we're gonna do tomorrow, but we're gonna have at least 1 hour a review tomorrow too. Okay. And it's the first time I can even 20 exercise. Well, again, you can try to just follow the steps, like in the previous example. Tiffany, you're saying for number 3. Yes, absolutely, Tiffany. That's the correct answer for number 3. That will be negative or +1. Yeah. Yeah, number 2. Number 2, yes. Yeah, number 2, it's just you cannot really write this be like to e to like a e to the to some power. So for number 2, it's like just like number 4. So it's like you have like a different bases, and then so you have to apply a natural log to both sides. Okay, so number 2 is 0.35 exing. Number 2, let me see. Natural log 3 + 1 over 4. Yes, Xing, I think you have the correct answer for number 2. Yes, very good. Elizabeth, yes, Elizabeth for number 3, that's ± 1. Yes. So for number 2, guys, just apply the same trick. Apply natural log to both sides. Sean. Yes, very good, Sean. That's exactly the answer. That's very good. That's exactly the answer. Yeah, number 2.
Thank you.
Mhm. Oh, wow. It's already 8:47. Time is really going fast. I was planning to have like at least 1 hour and a half to do to start the trig. But it's gonna be less than that for sure. True. Yeah, that's a signal. I don't know if it's a signal. Yeah. I don't believe in signals, so I guess. Number 4, review. You got number 4? Okay, you're saying Uh, yes, I think that's correct answer. Um, absolutely, yes, very good. Yeah. Yeah, so this is gonna be in the final for sure, guys. So you're gonna have some log equations, exponential equations for sure. Um, and then the last problem is gonna be about trig.
Is homework 6 available already?
Oh yeah, yeah, it's on Blackboard. Yes.
Is there trigonometry problems in that one?
Yeah, there's one problem, just
All
one
right.
problem. Yeah, I'm supposed to cover. I mean, I'm supposed to do like a little bit of trigonometry tonight, and I don't know if I'm gonna. I hope it's gonna be enough, like so then you can do the problem in the homework.
All right.
Um, does anyone need more time, guys? What? What did you say, Norton? Let's see. Tell if you know. Oh yes. All right. 2 minutes. Okay. I mean, we are not really in a rush. I mean, it's fine. Uh, Okay, you have 1 more minute, guys. Okay, right, I guess you're done with the exercise. So, so for number 1, we do have the same base, which is 7, right? This is 7 to the power x plus 1 equal to 7 power 2x. So same base, which is 7. So then the exponents are equal. Okay, so then the exponent, first exponent is of course x squared plus 1. Second exponent is going to be 2x. So that's like x squared plus 1 equal to 2x. All right, and then so I'm gonna just subtract 2x on both sides. So then I get like a quadratic equation, right? So that's like x squared minus 2x plus 1 on the right side, and just 0 on the left. Sorry, on the left side, and just 0 on the right side. So this is a quadratic equation. Just use a quadratic formula, or you can factor if you know how to factor this. So x would be like minus b, that's minus -2, plus or minus square root of b squared, that's -2 squared, minus 4 times a, which is 1, times c, which is also 1, over 2a. That would be 2 times 1. Right, so that's x would be minus -2, that would be plus 2. Right, this is a minus minus, that would be a plus. So that's plus 2, plus or minus. And under the square root, we're gonna have like -2 squared. That's -2 times -2, that would be positive 4. And minus 4 times 1 times 1, of course, is just 4. So this is actually 4 minus 4 over 2, which is of course 2 plus or minus. So 4 minus 4, of course, is 0. Square root of 0 is just 0. So it's just 2 over 2. So then we have only one solution here, which is x equal to 1. So the answer, so x is equal to 1. Right? Any question, guys, about this number 1? For number 2, it's different. So number 2 is e to the 4x minus 1 equal to 3. So for number 2, it's e to the 4x minus 1 equal to 3, right? So on the left side, it's an exponential with a base. So this is exponential. The base here is equal to e. Okay. Again, use just some decimal number. On the right side, it's not, well, it's 3. I mean, you can write 3 like, you know, 3 to the power 1 or wherever, but it's not, we don't have the same base here. So this is not the base here. So base here is not e. Okay. We have 3. So it's not the base, it's not e, right? So the base here is not e. And I cannot really write 3 like e to the power 0 or e to the power 1, right? So I cannot really express this 3 as some power of e. So yeah, so then the right side is not like, it's not a base there, it's not e. So we don't have the same base here. So not the same base. And so if it's not the same base, the idea is to apply natural log to both sides. So this is like e here, the power for x minus 1. This is just a p. And what I'm going to do, I'm going to apply natural log on the left and natural log to this p here on the right side. All right, so once you apply this natural log, so the idea would be to bring down this power because it's, you know, it's, so when you have, you know, when you have like a log in base b of x to the power a, you can bring down this power in front of the log. So that'll be like a times log in base b of x. Okay, so this power here, I can put down this power here in front of the log. So that will be 4x minus 1 times. So if you pull out this 4x minus 1, then you are left with there's this natural log. Don't forget the natural log. There's this natural log, and inside the natural log there will be e. Okay. On the right side is equal to natural log of e. Okay. Here, guys, we can simplify natural log of e. Just to remind you, log in base b of b, right? We said it's equal to 1, right? Log in base b of b is equal to 1. So natural log, that's a log in base base e, right? So natural log of e, this is like log in base e of e. Okay, so as you can see, if you have the same base and the same thing here inside the log, then the answer would be 1. So the answer here would be 1. Okay, this is the same thing here, e and e here. So this natural log of e is equal to 1. Yes, Joel, natural log of e is equal to 1. So this natural log of e is actually 1. So this is actually 4x minus 1 times, and we just said that natural log of e is 1, so this is actually times 1 equal to natural log of e. Okay, and so this is just times 1, so it would be the same thing, which is 4x minus 1, and on the right side is natural log of e. Okay, and again, natural log of e, if you use the calculator, there'll be like some decimal. I think it's 1.098 or something, right? And so now I'm gonna solve for my x. So all I have to do is just add +1 here, both sides. So this is like 4x equal to this natural log of e +1, and then finally to get rid of the 4, I'm going to divide the whole thing by 4. So it's just x on the left side equal to natural log of e +1, the whole thing divided by 4. So that will be my x, and then that's the final answer. Okay. And again, you can try to approximate this answer if you want. Natural log of e will be 1 point something. So this x would be approximately 1/2. All right. Is there any question, guys, about this number 2? So as you can see in this number 2, because we have different base, then we apply this natural log. Now for number 3, it's the equation number 3. So we have 6 to the power x squared minus 1 equal to 1. So for number 3, it's 6 to the x squared minus 1 equal to 1. Sean, you got, yes, I think you're correct, Sean. All right, so here it
Thank-
looks like we, welcome, sure. So here it looks like we have different bases, but it's not, because well, of the left side, of course, the base is 6, right? This is the base is 6, but 1, you can, the thing with 1, I mean, 1 is a kind of special, because you can write 1 as base is equal to 6. You can write 1 as like 6 to the power 0. That's the thing about 1. So it's very special in this sense. So you can write 1 as 6 to the power 0. And now, as you can see, we have the same base. So now we have the same base. So this is very special to 1. Okay, like in the previous problem, we had 3, and so you know, you cannot really express 3 as like e to some power. But here, 1, you can write 1 like e to the power 0 or 6 to the power 0 or whatever base you have, right, to the power 0. Right, so this is also base 6, and so if the base is if you have the same base, then the exponents are equal. So the exponent on the left side is this x, sorry, is this x squared minus 1, and on the right side the exponent is 0. So that's x squared minus 1 is equal to 0. And so then plus 1 both sides. You just x squared on the left, plus 1 on the right, square root both sides, and because the power is even, again, you're gonna need the plus or minus. So your x would be plus or minus positive 1. I mean plus or minus 1. Okay, so that's a fine answer. Okay, so again, this is very special to 1 because you can write it like 6 to the power 0 or e to the power 0 or whatever base to the power 0, right? But if you have like a different number, like a 3 or 4 or 5, you cannot really write it like some power, you know, 6. Anyway,
If you still add the natural log, it will still get you the same answer.
oh yeah, sure. If you
Do it
apply
that way.
natural log, yeah. The
Right.
thing is,
I know it's like a little shortcut. I would rather do it like.
oh yeah, this is like a shortcut. But if you apply, this is actually a good point. I mean, this is a very good question. I mean, I actually I had probably I need to make like a comment about that, because if you just apply, I mean, this natural log, applying natural log to both sides is like a very general way to solve any exponential equation. So like even in this case, even if you didn't write like 1 as 6 to the power 0 and you want to just apply natural log, you can do that. And I mean, let's do it. So natural log here and natural log here. So on the left, it's 6 x squared minus 1, and here it's a natural log of 1. And actually, natural log of 1, the log in base b of 1 is always 0. Yeah, this is log in base b of 1. This is always 0. So in particular, natural log of 1 is 0. So this is equal to 0. Okay, this natural log of 1 is going to be 0. On the left side, you can of course, you can bring down this exponent here in front of the log. So that would be like you know, x squared. Probably I should erase this thing here. So I'm going to write it somewhere else. So here, so log, oops. So log in base b of 1, log of 1 is always 0. In particular, natural log of 1 is 0. All right, so then here on the left side, I'm going to have like x squared minus 1 times this natural log of 6 equal to 0, right? So we have like, so what we are saying is like we have x squared minus 1 times this natural log of 6 equal to 0, right? So you have the product of two factors equal to 0. So either the x minus 1 is 0, the natural log of 6, it cannot be 0. I mean, natural log of 6 is some decimal. It's some positive number. I mean, if you check with the calculator, this natural log of 6, it's just some number, which is not 0. It cannot be 0. It's not 0. So actually, you end up with just x squared minus 1 equal to 0, and you get the same, you get the same solutions. So x is plus or minus 1. Okay, because this, again, this natural log of 6 is not 0, right? So then the x squared minus 1 has to be 0. So you see, even if you apply just the natural log both sides, you're gonna still have the same answer, of course. Is there any other question, guys? So log of 1 is always 0. Log of b in base b is 1. Okay, this is like two, very common identities. Identities that you need to know, I guess. Anyway, so for next, if there are no questions, for number 4 and last equation, which is, let me just find the last equation, which is, yes, the 2 to the 3x plus 1, 5x minus 1, so number 4. So here clearly we have different bases. So for number 4, so it's 2 to the power 3x plus 1 equal to 5 to the power x minus 1, if I'm not mistaken. All right, so here clearly we have like different bases. This is base 2 on the left, base 5 on the right. So we the only option here is really to apply a natural log to both sides. So here I have my 2 to the power 3x plus 1, and here I have my 5 to the power x minus 1. And the point of applying a log is that we can bring down this power in front of the log. So this power here, this exponent in front of the log, sorry. So there'll be 3x plus 1 times, and then there is still this natural log, and there's this 2 inside the natural log. So this is times natural log of 2, right? Equal to, here bring down this x minus 1, sorry, times, and then there's still this natural log and this 5. So this is natural log of 5. Okay. And again, guys, just think of this natural log of 2 and natural log of 5 as just some numbers, some decimals. So, and now, of course, so we need to distribute. So this thing here times natural log of 2 and 1 times natural log of 2, here's the same thing, times this natural log of 5. So that would be 3x times natural log of 2. There's a plus here, so it's gonna be a plus 1 times natural log of 2. On the right side, it's x times natural log of 5. And there's this minus, so it's minus 1 times natural log of 5. All right. So I got, there's an x in here, sorry. There's an x in here on the left side, there's an x on the right side. So again, guys, the idea would be to move all the x's on the same side, right? So I'm gonna move, let's say, for example, this x times natural log of 5. So just do the opposite operation. So there'll be minus x times natural log of 5 to the both sides. So minus x natural log of 5. So on the left, we're gonna have 3x times this natural log of 2, and then minus this x times natural log of 5. And of course, there's this 1 times natural log of 2, which is just natural log of 2. Equal, and then minus, there's this minus here, so minus 1 times natural log of 5 is just minus natural log of 5. Okay, so now I got an x in here, so the x will be like a common factor, so I can factor out x, but then there's no x in this natural log of 2, as you can see, right? This natural log of 2 is just some constant, some number. So I'm gonna move it to the other side. And the way to move to the other side is to do the opposite operation. So this is plus, so it's a minus now. All right, so then it cancel out here. And now I got this 3x, sorry. So I got this 3x times natural log of 2 minus x times natural log of 5 on the left, and on the right, that will be natural log of 5, minus natural log of 5 minus natural log of 2. Okay, this is good because now x is a common factor here and here. So you can just pull out the x, it's a common factor. So here's my x as a common factor, parentheses. And then I have this, if you pull out x here, you are left with this 3 times natural log of 2. So here it's going to be 3 times natural log of 2. There's a minus, this minus here, so here's my minus. And then the second term, if you pull out your x, you are left with this natural log of 5. So minus natural log of 5. And the right side is just, it's going to be the same thing. So minus natural log of 5 minus natural log of 2. And now, so it's x times this number between the parentheses. We don't care what the number is. So to get rid of that number, just divide, do the opposite operation, right? So divide by the same thing. So I'm going to divide by this 3 natural log of 2 minus natural log of 5. Okay, both sides, of course. So 3 natural log of 2 minus natural log of 5. Okay. And so this thing here, because we divide, so top and the bottom, we have the same thing, so it cancels out. So it's just x on the left equal to this minus natural log of 5 minus natural log of 2 over 3 natural log of 2 minus natural log of 5. And that'll be a fine answer. Okay, guys, so, and again, as I said, natural log of 2, natural log of 5 is just decimals. You can approximate this as x using a calculator if you want, but you don't have to. I mean, this is, I would say this is the best and the most compact answer, let's say. All right, guys, is there any other questions about this? So this is, I think we covered all possible exponential equations. I mean, all possible situations.
Professor,
Yes, excuse me?
Since the whole numerator is negative, shouldn't we like factor that out and put the negative in front of the fraction?
Yes, you can do that, absolutely. So you can factor out this minus, absolutely. So you can say, well,
yeah, I guess that's what I got.
yeah. So you get, absolutely, yeah. You can say this x is actually, this is a minus here in front of the fraction. So, and here in the top, like minus this. So this plus here, and yeah.
Okay, right.
Mhm.
Come on, Sean, you're trying to add more to that?
Well, isn't that the real answer? No.
Which
Damn,
one? No,
son.
they're the same. No, they're just the same. No, that's the real answer. And this, both of them are correct. Yeah, for real. All right. Any other question, guys, about this? So as I said, we cover, I think, all possible exponential equations. So basically, there are like two cases when you have like same base and when you don't have the same base, right? And that's it. All right, so we are done, I think, with the exponential and logarithmic equations. As I said in homework number 6, the first problem, it's about so these equations, and it's going to be also in the final, of course. All right, guys. So we are done with this section. So next, we're going to discuss a little bit the trig. So we have like so this is now it's like we have like how much, like 35 minutes. I'm gonna just probably discuss, I'm gonna just introduce the trig functions in the last 35 minutes, and tomorrow I'm gonna explain how to find or how to evaluate like the cosine and sine of any angle. All right. So let's move to the section, chapter 4. It's about trig. So we're gonna try to do, I'm gonna try to combine section. I know, Joel, I know you're upset. No, it's not that bad. You'll see, it's not that bad. It could be worse, actually. I mean, if we had like more time, like 1 or 2 more days, we'd probably try to solve trig equations, and that would be kind of tricky. But because we don't really have too much time, we're gonna just like do some very, I think, not really tough. Yeah. All right. So in this chapter 4, so we're gonna try to combine these sections, 4.1, point 2, and point 4. All right. So I'm gonna first. So this is the trig. Trig functions and unit circle. Okay. So I'm gonna start with the definition of the angle. So we're gonna measure, the angles using units. I'm gonna use degrees or radians. So I'm gonna discuss first relation between the radians and degrees, and then I'm gonna introduce the trig functions, cosine, and etc. So first, what's an angle? So an angle is just is formed by, so an angle is formed by two rays that have a common vertex. So you have your vertex here, right? And then you have like an initial side, and there is a terminal side. So this one here, let's say this one is the initial side, right? And this one here, this arrow here, is the terminal side. Terminal side. Okay, and so you go from the initial side to the terminal side. So like in this case here, of course, you're going to go from this initial to this terminal side, and this will be your angle. So your angle. Okay. And actually, we have like positive angles and negative angles. Depends on the rotation. So there are two possible. So if you have a counterclockwise rotation, so what do I mean by counterclockwise? So like in this case here, you go from, so this is your initial side, this is your terminal side, this is the initial, this is the terminal side. So in this case, this would be, this angle here is going to be a positive, right? Because it's a counterclockwise. So this is positive angle. But if you have like a clockwise rotation, then that would be a negative angle, right? So when you have clockwise. So again, you have this vertex here. You have your two sides. But now, let's say the one on the left would be your initial side. Let's say this one here is the initial side. And the other one here on the right would be the terminal side. Now we go from initial to the terminal side. So you get like a clockwise rotation in this case. Right, this would be clockwise. And so this angle in this case would be a negative angle. So this is a negative. This is a negative angle. So all I'm saying, guys, here is that an angle, it could be positive or it could be, it could be positive or it could be negative. Okay, so it's possible for an angle to be negative. If you have a clockwise angle, that would be negative angle. Okay, so that's what you have to keep in mind, right? So angles, they can be positive or negative. All right, now how do we measure angles, right? That's now the next question. Oops. So how do we measure Am I recording? Yes. Okay. How do we measure angles? So in other words, I mean, which units we use to measure angles, right? So we have two possible units. We can use degrees or radians. So we can use degrees. Okay, or radians. Okay, now, for example, let's take very special angles. Okay, so here's my vertex. All right. Now, first kind of special angle, of course, would be the zero angle. So, if your initial and terminal side, so the red, here, as you can see, the red, so the red arrow here, that's my initial side. And what I'm saying is that my initial side and terminal side are the same here. Terminal side and initial side, they coincide. Okay, so it's like they coincide, right? The terminal and initial side, they coincide. So in that case, the angle would be just the angle. It's just the angle 0, right? So this is just. So in this case, this is just the angle 0. Okay, so this is the angle 0. So the angle 0 is when, the terminal and initial side, they coincide. Now, next, if you go from this initial side to this terminal side, so this angle here, this one here, this is a right, of course, this is a right angle. And as you know, right angle in degrees, that it will be 90 degrees. So this is a 90 degrees angle. Of course, the symbol here for degrees is this circle, right? This circle here means degrees, right? So degrees, this is just a symbol for degrees. Okay. Okay, so that's the right angle. That's in the 90 degrees. Now, if you go from so this this initial side to the opposite one. Okay, so this the yellow angle here. So this yellow angle would be, will be 180 degrees, right? This is 180 degrees. Okay. And then if you go one more 90 degrees, let me probably take a blue now. So if you go like from here to here, you stop at this terminal side, all right, then that will be 270 degrees, right? So this is 270. Okay, and now if you have like one full rotation, if you go from, let's use a different color. So this one here. So if you do like one full rotation, right? You go like from here and then you stop at the same side. One full rotation would be, of course, 360 degrees, right? So this is a full rotation, and the full rotation is 360 degrees. Okay, is 360 degrees. Okay, so right angle, that's 90 degrees. If you go from one side to its opposite, that will be 180, and then there's 270, and then one full rotation would be 360 degrees, right? So this is kind of like very special angles. Now, as I said, we can measure angles using degrees or radians. Now, what's the relation between degrees and radians? Well, the thing is 360 or 180, let's say 180. So 180 degrees is equal to pi radian. So the relation between degrees and radians. So 180 degrees is equal to pi radian. And I mean, if you multiply by 2, of course, 360 degrees would be like, 360 is twice 180, all right? So 2 times 180, so that's 2 pi, 2 times pi. So that's 2 pi radian, right? Of course, if you have 90 degrees, 90 degrees, that's a half of 180. So that's half of pi, right? So that's pi over 2. That's pi over 2 radian. Okay, etc. So how do we convert degrees to radians? So how do we convert degrees to radians? So you just multiply by pi over 180 degrees to radians. Okay, just multiply. So the rule is to multiply by, as I said, pi over 180 radians. Okay, so for example, let's say I want to convert example. Let's say I want to convert 50 degrees to radians. Okay, so you take 150 degrees and then you multiply this 150 degrees by pi over 180. 180 degrees. Okay, so this is now like 150 over 180 times pi. And then you can simplify, you have to reduce, right? You have to reduce this fraction here. So you have to reduce the fraction. Reduce the fraction. Okay, so the 150 over 180, you want to reduce a fraction. For example, you can divide the top and the bottom by 10, for example. By 10 here, and by 10 here. So that will be equal to 15 over 18 pi. We can still reduce this fraction because 15 and 18 both are divisible by 3, right? So we can divide absolutely, Diani. So we can, both are divisible by 3. So then the answer 15 over 3 is 5, and 18 over 3 is 6. So that's 5 over 6 pi. So the answer here, guys, so 150 degrees, 150 degrees would be 5 over 6 pi. So, or 5 pi over 6. Okay. So from degrees to radians, you multiply by pi over 180. Now, the other way around, if you want to convert radians to degrees, and now to convert, so to convert radians to degrees, you just multiply by the reciprocal, so which is 180 over pi. So radians to degrees, 2 degrees. So you just multiply. So the rule is to multiply by 180 over pi. 180 degrees over pi. Okay, so for example, let's say you want to convert 2 pi over 3 to degrees. 2 degrees. All right. Let's see. So this is 2 pi over 3, and as I said, the rule is to multiply now from radians to, of course, this is radians 2 pi over 3 to degrees. So we multiply 2 pi over 3 by 180 degrees over pi. Yes, Joel, absolutely. That is going to be 120. So as you can see, guys, here there's a pi in the numerator and there's a pi in the denominator. Okay, and of course this is a product. Okay, so because if it's a product, you can cancel out the pi in the top and in the bottom. So this is just now 2 times 180 degrees over 3. So that will be equal. So 2 times 180, that will be 360 degrees over 3, and 360 over 360 degrees over 3. As Joel said, that will be 120. Okay, so that's the answer. So 2 pi over 3, that's 120 degrees. 2 pi over 3, it's 120 degrees. So as you can see, Joel, it's not that bad. So All right, so here's an exercise for you because we need to know how. Okay, you still remember this. That's good. So yeah, this is a small exercise, guys, because we're gonna need to know how to, convert degrees to radians and radians to degrees. That's it's kind of important. So here's a small exercise for you. Just convert. So first, exercise one. So one. So please try to convert to radians.
This is the exercise that is going to the exam.
No.
Oh, I don't know. Yeah, this is too easy, right?
It's
Dang.
too easy. It's too easy. Yes. It's still too easy. Yeah. Yeah. But because we're gonna need this later. So convert to radians. Yeah. So let's say number one, number two. So let's say here first, we have here for number one. Let's see. Yes, 210 degrees. All right, and let's say 300 degrees. Okay, so please try to convert this to radians. And number two, convert to degrees. Degrees, pi over 4, right? And 7 pi over 6. 7 pi over 6. Right, guys? So I'm gonna just give you a couple of minutes to think about this. So we need this, this relation between degrees and radians because you're probably familiar more with the degrees. So it's good to know this relation between degrees and radians. Norton, you're saying 7 pi over 6 for number one, which is absolutely correct. Very good, yes.
Which gives you number 2 from exercise 2.
That's right. That's right. Actually, I didn't I didn't really do it on purpose. That's right. All right, guys. I guess probably this is too easy for you. So for the 210, as Lorden said, so if you multiply, by pi over 180 and you reduce the fraction, so it's going to be 7 pi over 6. Lorden, you're saying for next, it's 5 pi over 3. Let's see. 180. Yes, absolutely, of course. Yes, of course. For number two, as Lorden said, it's 5 pi over 3. For number two, as I think Joel said. 7 pi over 6, of course, is just the same thing as number 1 here. So this is 210 degrees. And for pi over 4, that's, yeah, Lord, absolutely. That's 45 degrees. This would be 45 degrees. Okay. All right. So we have this relation between degrees and radians. That's good. Now, next, I'm gonna introduce the trig functions. So now the fun part is gonna start. Unit circle. Well, we have like 10 minutes. Of course, in 10 minutes, I cannot really do a lot. Okay, I'm gonna just briefly talk about, just to introduce the trig functions, and then of course tomorrow I'm gonna continue with this, and hopefully I'm gonna be able to cover at least one of the exercises in the review sheet. So the unit circle, guys, what I mean by unit circle, it's a circle of radius 1. So we take you have this is your x-axis, or is this 0 somewhere, and let's say here's 1 right here, 4, and here's my y-axis. Of course, here somewhere here it's 1. This is -1, and here it's -1. So the unit circle, that will be a circle of radius 1. So we're gonna have this circle, which passes through the +1, and here the -1. Okay. So unit circle means a circle of radius 1. Unit circle, that's a circle of radius 1. So the radius, of course, that's the distance from the points of the circle and the center of the circle. Like, so here, of course, the center of the circle would be the origin. This is the center. This point here, this is the center of the circle. And I mean, if you measure the distance between the origin, the center of the circle, and any point of the circle, distance would be 1, right? So, for example, from 0 to 1 here, that's 1 unit. Okay, that's what I mean by radius equal to 1. All right. Now, what I'm gonna do, I'm gonna take an angle in this unit circle. So let's say this is my initial side here, and somewhere here, this is my terminal side. All right. And so we have an angle theta. So let's call this angle here. So this is my angle theta. All right. Now, guys, I mean, if you take this, there's a right triangle here. So if you take this right triangle, this one, let me pick a color. So let's go with yellow. Okay, so if you take this right triangle, the yellow one, okay. Again, this is here. This is your angle theta. Okay. So we have this. This is the right. Of course, this is the right triangle. So what do I mean by, of course, right triangle is one of the angle is 90 degrees, right? So this is the right triangle. So we have this. So this is here, this is of course here, this is 90 degrees, right? And here, this is my angle theta, right? This is my angle theta. All right. Anyway, so in this right triangle, of course, there's this point here, this point here, which is one of the vertex of my right triangle. So this point here, let's call this point the point XY, right? This is a point. So this is the point. This is the point XY. So the X coordinate, as you know, this is the X coordinate will be here. All right, probably I'm gonna pick a different color. So the X coordinate is here, and the Y coordinate would be here. Okay, so that's the point XY. Anyway, so I'm gonna define first sine of theta, sine of the angle theta. So I'm gonna probably erase this here. Okay, so let's define sine of theta. So sine of theta would be, by definition, sine of theta of the angle theta would be, by definition, the opposite side to the angle theta over the hypotenuse of the right triangle. So this is by definition, this is the opposite side over the hypotenuse. So what do I mean by the opposite side? So again, we have this right triangle, right? This yellow triangle. This is my right triangle. So here I'm supposed to have my theta. This is my angle theta. Here, this is my right angle. Okay, and so this is my right triangle. Now, what's the hypotenuse of this right triangle? Well, this side, this one here, this side is the hypotenuse, right? This is the side which is opposite to the right angle. That's why I call the hypotenuse, right? This is the side opposite to the right triangle, right? So this is here's your right, this is your 90 degrees, right? And so the opposite side to the 90 degrees is the hypotenuse. That's what I call the hypotenuse. All right. Now, what will be this the opposite side to the angle theta? So opposite side of theta, of course, here. This is opposite side of theta. Oops. Of theta. So opposite side of theta would be, of course, this this side here. Right. So this is the opposite side of the angle theta. Okay. So by definition, sine of an angle theta in a right triangle, that would be the opposite side of theta over the hypotenuse. Okay. Cosine of theta cosine of theta. So by definition would be the adjacent side of the angle theta, adjacent side over the hypotenuse. So where would be the adjacent side? Well, it's the side which is next to the angle theta, which is not the hypotenuse, of course, but this one here. This is the adjacent side to the angle theta. Adjacent side. That's what I call the adjacent side, right? So that's the definition of the sine. sine of theta. So we have to measure, I mean, in theory, so if you want to compute the sine of any angle, so what you do, you take a right triangle, and you measure like the opposite side of the angle over the hypotenuse, and that will be your sine. And the cosine would be like in your right triangle. So the cosine of the angle theta would be like the adjacent side. You have to measure your adjacent side, and you divide by this hypotenuse. And next, of course, once you have definition of sine, cosine, you can define tangent of theta as a sine over cosine, etc., etc. You know what, guys? I guess I'm gonna stop here because there's a lot to say now, and we don't have time. I mean, it's 55, so I'm gonna stop here, and I guess I will see you tomorrow. All right, guys. Good night, everyone, and thank you for listening.
Good night. Thank you.
Good night.
Good night.
See you tomorrow. Take care, everyone.
Hi, guys.
Good night. Bye.